who are at home, the first thing that we're going to do right away here this afternoon is to go over the homework questions from yesterday. So the sheet that I gave you guys, we went through the first 10 yesterday, right? Okay, yeah. So we just need to go through 11 through 20 on both sides of this sheet from yesterday. So give you just a moment real quick to pull that up, pull it out, whatever you need to do to make that happen. And then I will go through the answers here in just one moment. While you're getting stuff out, would be a real good idea for you to have your periodic tables, your polyatomic ion sheets in front of you. All right, here we go. Number 11 is potassium permanganate. 12 is tin 2 dichromate. And that 2 would be a Roman numeral. So tin, Roman numeral 2 dichromate. Number 13 is boron tetrachloride. 14 is dinitrogen tetroxide. 15 is diiodine dichloride. Number 16 is strontium bromide. Number 17 is sulfur dibromide. Number 18 is sulfurous acid. '19 is cobalt 2, that's a Roman numeral 2, phosphate. And 20 is hydrosulfuric acid. Hydrosulfuric acid. All right, then on the back side, now you had the names and you needed to write the formulas. Number 11 would look like PB, parentheses, NO3, and then a 2 after it. PbNO3, 2. Number 12, very similar, is Mn, parentheses, NO3, 2. Number 13 is CH5. Number 14, we're going to have parentheses around NH4, and then a 3 after that, and then PO4. So NH4, 3, PO4. '15 is HCl. 16 is Sb2Cl6. 17 is N5O10. 18 is N2H4. 19 is HNO2. and 20 is MGS. Does anybody need to ask me any questions about any of the homework problems? Okay. All right. We're going to learn some new stuff. So you probably want to take notes. So give you a couple seconds to get stuff out to take notes with. While you're getting stuff out, this is the last of the new stuff for this unit. So we'll be having a test next week. My goal is for the A group to have it on Tuesday, the B group to have it on Thursday. It's kind of my plan. Okay. So when we started this unit, the very first thing we started with were electron dot diagrams. You guys might hopefully remember that we used the element symbols and we put dots around them to represent the number of valence electrons. And then I used those dot diagrams when I taught you how ionic bonds happened, right? Metals would give away electrons to become cations. The nonmetals would accept the electrons and become anions. And then those opposite charges would attract and form an ionic bond, et cetera, et cetera. Okay, so we're going to use those dot diagrams again today to look at how the covalent bonding process is going on, more or less. Okay, and so we're going to start. Let's start with fluorine. All right, so find fluorine on your periodic table. How many valence electrons does it have? How many valence electrons does fluorine have? 7 is right. You're counting from the left side of the periodic table, right? 2 in the S, 5 in the P. Okay? So I'm going to represent those 5 electrons. I probably need to write a little bit bigger. And I also probably need to point this down a bit. All right, so there's fluorine's 7 valence electrons. Now, if we think back to what we did with ionic bonding, what does fluorine going to probably want to do to get stable? Gain 1 electron, right? Okay, but of course it can only do that if there's an atom that wants to give electrons, right? What if the only other atom around is another fluorine atom? Would 2 fluorine atoms be willing to give up or to take electrons from each other? No way. Okay, in fact, if you go back to the last unit we studied, we talked about electronegativity values, and that is the atom's pull on the bonding electrons, right? And so fluorine, since these are both the same type of atom, they're going to have exactly the same pull on any electrons for each other. So there's not a situation where one could give or take, but in order to be stable, instead of giving and taking, of course, they can share, right? And so that's exactly what they're going to want to do. There's a pair of electrons right here, and those 2 atoms can easily share that pair of electrons. And then if you look at it from this standpoint, now this fluorine atom has 2, 4, 6, 8 electrons, right? And this atom over here has 2, 4, 6, 8 electrons because of the sharing thing. And now everybody's happy. And so what we've done is to create now a covalent bond. That's when electrons are shared between atoms. Okay? And this has a couple of other descriptive names that we can use with it. First of all, this is called a single covalent bond. And we call it that because we're sharing one pair of electrons between the two atoms. Okay? So a single covalent bond sharing one pair of electrons. And when we draw this thing up here is called a Lewis structure for this molecule. When we draw this Lewis structure, we take those electrons that I circled that I was showing you were going to be shared, and we replace them with this single line. And that line represents my shared pair of electrons, okay? So when you come across a line like this in a molecule, you're going to understand that that means a shared pair of electrons. And if I've got just that one line, that's one shared pair of electrons or a single covalent bond, all right? Now, going back to what I said just a few moments ago, when we were talking about electronegativities, again, since these are both the same type of atom, since they have an equal pull on these two electrons, the electrons are going to be shared very much equally between the two atoms. And that has another descriptive name to it. So this is called a non-polar covalent bond. Non-polar covalent bond. And again, that simply means that the electrons are being shared equally or almost equally in some situations between the two atoms. So I can use all of these words together to describe what's going on here between these two fluorine atoms. So this is a single non-polar covalent bond. And that's very, very descriptive then. Tells me lots of information, right? Tells me that there's one pair of electrons being shared and that they're being shared equally between these two atoms. Single non-polar covalent bond. All right? Anything that you need to ask a question about? Is anything unclear there that I've said? Okay. Let's look at a different situation. Let's take a look now at oxygen. Can you please tell me how many valence electrons an oxygen atom has? Six, yes, thank you. All right, 2 in the S, 4 in the P, right? So let me put those up here. Again, based on what we did with ionic bonding, oxygen would tend to want to do what to get stable? Gain 2 more electrons to get to that octet, right? But again, I pose the question, what happens if there's no other atom around that will give electrons? For example, what if the only other atoms are other oxygen atoms? So what will this thing do to get stable? Well, if fluorine could share one pair of electrons to be stable, is it reasonable that oxygen could share 2 pairs of electrons to be stable? Yes, many of you are shaking your heads yes at me, or nodding, I guess I should say. Good. Okay. So now, this represents what we would call a double covalent bond. 2 pairs of electrons being shared between the oxygen atoms. So again, each line represents a pair of electrons. I'm sharing 2 pairs. So this is a double covalent bond. Now I still have these unshared pairs of electrons, so I'm going to put those in. All right, these unshared pairs of electrons are just that, electrons that are still hanging out around oxygen, but they're not being shared at all. They just belong solely to this oxygen. So now as we look at each atom, watch me here as I do this. This atom has 2, 4, 6, 8 electrons around it, so it's got its octet. The same way, this oxygen atom has 2, 4, 6, 8 electrons around it, so it has its octet. And because of the sharing of the 2 pairs of electrons, this double covalent bond, both atoms are now stable. Again, I want to point out to you that both of these are the same type of atom, meaning their electronegativities are identical again. And so this also is a nonpolar covalent bond because those electrons are going to be shared equally between the oxygen atoms. Okay? So each atom has 2 shared pairs of electrons and 2 unshared pairs of electrons. Our fluorine example that I've already erased, but that had 1 single covalent bond, right? 1 shared pair of electrons, and then 3 unshared pairs of electrons around each atom. Find nitrogen on your periodic tables, please. How many valence electrons does this thing have? 5. Very good. Thank you. Excellent. All right. Let's put them up there as dots. Okay. In order for nitrogen to get stable, based on what we learned when we dealt with the ionic stuff, what's it going to tend to want to do? How many? 3 more electrons, right? Again, what happens in the situation where there's not another atom willing to give it 3 electrons? For example, what if there's only other nitrogen atoms around? Well, by the theorem of least surprise, nitrogen will form a, what should we call this? Triple covalent bond. Very good. Nice work. Yep. So nitrogen is going to form a triple covalent bond, sharing 3 pairs of electrons between the 2 atoms. All right. And so again, if we look at each of these atoms individually, follow me here. This nitrogen atom has 2, 4, 6, 8 electrons around it. And this other atom over here has 2, 4, 6, 8 electrons around it as well. So they both have filled their octets and are going to be stable. 2 atoms have the same electronegativity. So again, this is also an example of a nonpolar covalent bond. Electrons are going to be shared equally between these 2 atoms. Single, double, and triple covalent bonds in that order are in order of strength also. Single covalent bonds tend to be easier to break than double covalent bonds, which tend to be easier to break than triple covalent bonds. This right here is an incredibly stable molecule. In fact, this is what makes up almost 80% of the air around us. And it's very, very, not like a noble gas unreactive, but very unreactive compared to many other things, okay? Very stable, sharing 3 pairs of electrons. Takes a lot of energy to break a triple covalent bond. So if I want to separate this and do something else with it, it's going to require the input of a large amount of energy to make that happen, okay? Any questions thus far about these bonds? All right. So we've been talking about nonpolar covalent bonds. I want to take just a minute to look at the other side of the coin. And I'm going to use water as my example. Might as well. We're all very familiar with it. Okay. Now, yesterday when we named this, we didn't call it water. What is a chemist going to refer to this as? It's a molecular compound, so we need prefixes. What's that? What's the prefix for 2? Di. Of course, this element is hydrogen, so dihydrogen. How many of these do I have? 1. What's the prefix for 1? Mono. Oxide, yeah, ends in IDE, so monoxide, dihydrogen monoxide. We're naming that using the rules, okay? All right, so let me draw this. Here's my water molecule drawn out, okay? So I keep talking about electronegativity values. We're actually going to use them and look at them for this substance so I can kind of figure out what's going on. So on my trusty periodic table that I have over here, I have electronegativity values for these 2 atoms. Oxygen's electronegativity value is 3.98. Hydrogen's is 2.20. Oh, I looked at the wrong ones. Forgive me. Sorry, that's not correct. I looked at fluorine. It's 3.44. Sorry about that. Okay. So again, this is just a value that's assigned to how strongly the atom's pulling on the bonding electrons, right? The higher the number, the stronger it's pulling, okay? So as you can see, oxygen is going to be pulling harder on the bonding electrons than hydrogen is. And if you remember when we talked about the trends in the last unit, there's really 2 things at play here. Number 1, the distance the protons are from the electrons in the atom. And number 2, the number of protons that are effectively pulling on the bonds, the electrons in the bond. So that effective nuclear charge that I talked about before, okay? So the more protons that are pulling on the electrons, which is the case for oxygen, right? It's got more protons than hydrogen does, so it's going to be pulling harder, even though the electrons are going to be closer to hydrogen's protons because it's only in the first energy level and oxygen's in the second energy level, but there's more protons, so it's going to be pulling harder, okay? So here's our 2 electronegativity values, and all we do, this is super simple, all we do is literally subtract them. So 3.44 minus 2.20 is 1.24. Okay, that's the difference between the 2 electronegativity values. Now, if you've done the reading in CK12, you've read, and there's a chart in there that shows you that if you have a difference in electronegativities of between 0 and about 0.4 or so, your bond will be nonpolar covalent. In other words, their electrons are being shared pretty close to equally, okay? If you're between about 0.4 to around 2, somewhere in that neighborhood, one atom's pulling harder on the electrons than the other atom is, and so that's going to be a polar covalent bond where the electrons are shared unequally. So that's what's going on in this case. My number's between 0.4 and 2, and so the atom with the higher electronegativity, which is oxygen, is going to be pulling harder on these bonding electrons, this shared pair of electrons, which means essentially they're going to spend more of their time closer to oxygen. And because of that, if you'll think about the idea of the ionic bond, if oxygen could take the electrons from hydrogen, what kind of charge would oxygen end up with? If oxygen could take the electrons from hydrogen, what kind of charge would oxygen have? It would be gaining electrons. So what would its charge be? Negative, right? And that would make hydrogen positive. It lost electrons, okay? But again, it's not quite strong enough to take the electrons. So it doesn't become negative and it doesn't become positive, but it's kind of on the way there. Since the electrons spend more of their time around oxygen, oxygen has a partial negative charge, and hydrogen, since the electrons are there less of the time, has a partial positive charge. Okay? And so our bonds are polar covalent bonds. All right? And so again, my pole is pointing towards oxygen. And by the way, this is the lowercase Greek letter delta. Again, if you did the reading in CK12, you've seen that already. Okay, if you haven't done that yet, you're going to want to get on that soon as the unit is coming to a close quickly. So we've got a partial negative charge on oxygen, again, because the electrons are there more of the time, closer to oxygen than they are to hydrogen. And we've got a partial charge on hydrogen, because the electrons are not there as much. They're spending more of their time with oxygen. Okay? And so we get this dipole. And the net dipole here, because of the shape of the atom, is that one side of the molecule is partially negatively charged, the oxygen side, and the other side is partially positively charged. And I have some models here to kind of help you visualize that, all right? So oxygen, hydrogens, the oxygens are white. The oxygens are red, the hydrogens are white, okay? So this is the shape. It's going to be a bent shape. That's our molecular geometry. And again, I'm just kind of introducing you. I'll use these words every once in a while just so you're exposed to them, okay? But because of the shape of this, you can kind of think about drawing a plane in space across here. This end is partially positive. This end is partially negative, right? So what does that mean? Why is that important? Well, these molecules, whenever they're around each other, they're going to be attracted just like this. You guys see okay? This end is partially positive. This end is partially negative. If you've got those partial charges, there's going to be an attraction there. And this attraction is called an intermolecular force. Inter is a prefix that means between. So a force between molecules, intermolecular force, right? And it's a force of attraction. And this particular force of attraction has a very specific name. It's called a hydrogen bond. And it's not a true bond like the ionic bond or the covalent bond. It's just an intermolecular force, but it's still a very strong force of attraction. So I want to make this point. Water at room temperature is a liquid. The reason is because of this attraction. Because water's shape, because of the polar covalent nature of the bonds, we get polar molecules. Because of that attraction, they want to be by each other, right? Well, when things are by each other in the state of matter, where they're by each other but still free to move around, that's a liquid. You with me? Okay. Now, think about this for a second. Replace oxygen with sulfur. It's right underneath it on the periodic table, same family, so it's going to behave just like it, more or less, right? But sulfur, because it's farther away from fluorine, you intuitively, I hope, know that its electronegativity value is lower. So the difference is not as much, okay? Which means the bonds are non-polar covalent. So if this was a sulfur instead of an oxygen, this would be a non-polar covalent bond, which means that the molecule is non-polar, which means there's no attraction here. This molecule would not be attracted to this molecule if these were sulfurs. If there's no attraction, that means they're free to just move past one another, right? What state of matter exists when particles aren't attracted to each other and they're free to move around wherever they want? Gases. H2S is a gas at room temperature. while H2O is a liquid at room temperature. And it's all because, ultimately, of the type of bond here, where the one is polar, water, the other, H2S, is nonpolar. Okay, and that changes everything. So it gives it a different state of matter at room temperature. All right, questions, comments, or concerns? All right, so the main things that I wanted you guys to pick up on today in class, the main ideas were single, double, triple covalent bonds, the sharing of 1, 2, and 3 pairs of electrons, right? I wanted you to be able to distinguish between a nonpolar covalent bond, that means the electrons are shared equally between two atoms, and a polar covalent bond, like the case of this molecule, where one atom's pulling harder, and that changes properties. Okay, that's the key that I want you to take away from that. That changes properties. Okay? So polar covalent, nonpolar covalent, single, double, triple bonds. Okay, so that's kind of the notes for today. Again, the test is coming up before you know it. So if you haven't read all the sections of the book yet, you want to get on that so that you are ready to go for the test. All right, your work assignment for today is on Google Classroom, and it's a worksheet, another worksheet that I typed up here the other day, and I'm calling this one the error worksheet. Now, this worksheet is very different from the other worksheets that you guys have been doing the last couple of days. Remember, I've been telling you that you need to practice until you can't get them wrong. That's right. Thank you. Okay. Well, here's the deal. On this worksheet, something is wrong. And your job is to see if you can figure out what it is. Okay. So if you want to pull up that worksheet real quick, so I can go through a couple of examples with you just to kind of help you see what I'm talking about. What I did is, and I don't have it in front of me, but I have, on one side I've got the chemical formula, and on the other side I have the name. Okay? Something doesn't match up. Something's not right. And basically what I did was I took things that, you know, when you take, for example, when you guys are learning stuff and you're making mistakes, that's like what I did on this sheet. What are common mistakes that students make when they're learning this stuff? Does that make sense? And so I put these kinds of mistakes on there to see if you could catch them. So here are some of the things that you can be looking for. Okay? And I did lots of different things wrong. Every problem's got something wrong. And I did lots of different things wrong. So maybe the formula and the name don't match for some reason. Okay? For example, maybe I've got a polyatomic ion with oxygen, but my anion name is IDE. If it's got oxygen, what should it end in? Look at your polyatomic sheet. What do they end in? ITE or ITE or ATE, right? Most of them end in ate or ite if they're polyatomic. So that's just an example. Maybe I didn't use a Roman numeral on a transition metal. Maybe when I wrote the formula, I didn't balance the charges, so the right subscripts aren't there. Maybe when I balanced the charges, maybe I wrote it as a superscript instead of a subscript. Okay, so I'm just kind of throwing some things out there. There's something wrong with every problem. You need to look at both the name and the formula. On some of the problems, and I'll tell you, for example, number one. This is number one. Either you could rewrite the formula to match the name, or you could rewrite the name to match the formula. That's number one. Okay, they don't match up, so you got to fix one or the other. Now, on some of the other problems, there's a very more specific thing wrong. For example, like I was saying, where maybe I used a superscript instead of a subscript, and you have to fix that. You don't have the choice. On some of them, you'll have a choice. Do I want to fix the left side or do I want to fix the right side? On other problems, there is no choice. There's only one thing that's wrong, and you got to find out where it's at. Okay? So that's your assignment. So you have the rest of class today to work through that assignment. Okay? Just put the correct thing next to or underneath or wherever you want to on the worksheet, but fix the problem. All right? So those of you who are at home, if you need me, I'll be here. Otherwise, you guys have a great weekend, and I'll see you in class on Monday.